Hi, this is Mrs. Villette, and in this video we'll put together everything that we've learned about first and second derivatives to make a detailed sketch of a curve. So this section is called curve sketching. We're going to go through just a series of steps, and we're going to use that to determine how to make a graph by hand, essentially, and then we'll check using technology. So the first step is going to be to determine the domain. So the domain controls things like where there might be vertical asymptotes or where there might be a removable discontinuity. Next, we find x and y intercepts. Then we find the vertical asymptotes, which are the zeros of the simplified denominator, which if you found the domain up here in step 1, this should be fairly easy. So far none of this is really calculus. Then you find the horizontal asymptotes, and the way we find horizontal asymptotes is we take x to infinity and x to negative infinity. Then we're going to find the critical numbers, and we will use those to figure out where the function is increasing and decreasing, and also the local extrema. And then finally we will find the critical numbers of f prime, so essentially we're finding the second derivatives, zeros, and undefined points, and that will tell us the intervals of concavity and the inflection points. So let's go ahead and start with an example of a rational function. We are asked to do detailed sketching on this function 2 times x squared plus 4x plus 4 over the square of x plus 3. So step 1, finding the domain. Now I can see in this problem that the only value of x that gives me any issues is if x equals negative 3. So my domain is the set of x such that x does not equal negative 3. Now, how do I know what type of discontinuity that is? In order to do that, which we'll do in step 3, we actually need to make sure that this function is fully simplified. But let's go ahead and do step 2, which is to find the x and y intercepts. So if you want to find a y-intercept, that's the easier one to find. You're just going to evaluate f of 0. So if I evaluate f of 0, I have a 2. These first two terms are just zeros. So I have a 4 and then 9. So 2 times 4 ninths, that's times, not 2 and 4 ninths, is 8 ninths. So I have 0, 8 ninths. If I want to find an x-intercept, you need to let your function equal 0. And this is where we might want to start working on some factoring of this function. So my denominator is x plus 3 squared. Then I have x squared plus 4x plus 4. Now I know that I can pretty much cross multiply that denominator, get rid of it. I'm really just looking for the zeros of the numerator. So let's go ahead and factor x squared plus 4x plus 4 is just the square of x plus 2. And that gives us that x equals negative 2. So my x-intercept is negative 2, 0. Now even though this is a rational function, we can use the ideas that we had from polynomial functions to determine because this has even multiplicity, my function should bounce rather than cross at that x-intercept. All right, step 3, find the vertical asymptotes. So we've already figured out that our function is actually the square of x plus 2 over the square of x plus 3. There's nothing that simplifies, so my vertical asymptotes are at the zeros of the denominator, which is at x equals negative 3. That is actually a vertical line at x equals negative 3. Step 4 is the horizontal asymptotes. So if I want to find the horizontal asymptotes, I need to take the limit as x goes to infinity of the function. Let's go ahead and go with this simplified version. I'm going to think about what would happen when I expand this function. When I expand the numerator, I'm going to get x squared plus 4x plus 4, which I already knew, but my leading term is going to be 2x squared. And then I have some stuff. And then in the denominator, my leading term is x squared. And then I have some stuff. Using just our trick of leading terms, this limit is going to end up being 2 because these were equal degree. So my horizontal asymptote, at least on the right, is y equals 2. Now for rational functions, the right horizontal asymptote and the left horizontal asymptote are going to be the same as each other. So I'm actually done on this. Now you should know that there are some functions where that's not the case. So an example would be the inverse tangent function has a different left and right horizontal asymptote. Also your logistic growth functions, which look sort of similar, have that same feature of having a different left and right asymptote. So for this case only, your rational functions, which just means polynomial over polynomial, have one horizontal asymptote. So now we get into the more calculus-based stuff where we are finding derivatives, finding critical numbers, finding second derivatives. So I'm going to go ahead and move to the next page. I'm going to put down the information that we have, and then we're going to continue with steps 5 and 6. So I've transferred the information over from the previous page. I've got my domain, x can't equal -3, which turned out to be a vertical asymptote. I've got my y-intercept at 8/9. I've got my x-intercept at -2, and then I've got my horizontal asymptote at y equals 2. All right, let's see what else we can figure out. We are now moving on to the portion where we need to start taking derivatives. So we'll start with writing down our function. And in order to take its derivative, we need to use the quotient rule. So we're doing bottom derivative of the top is going to be done with the chain rule and the power rule. So the derivative of the top is 2 times the derivative of the square function. Subtract the top times the derivative of the bottom, which is again chain rule, all over the square of the bottom. Now we want to be careful here and make sure that we don't go crazy with our cancellations. So the easiest way to make sure we do this correctly is to try to see what we might have as a common factor. If I look between both terms, it looks like I have at least an x plus 3 in both of them and at least an x plus 2 in both of them. So I'm going to go ahead and factor out x plus 3, x plus 2, and then I'm going to see what I have left. So from the first term, I have taken out the x plus 2, and I've taken out one of the x plus 3's, so I'm left with a 4 and an x plus 3. And in the second term, I have taken out one x plus 2 and one x plus 3, so I'm left with a 4x plus 2. And that makes me realize I could have also taken a 4 out, but we can deal with that in a minute. So there is one factor of x plus 3 in the whole entire numerator, so I'm going to reduce that down to a 3. And then I'm going to go ahead and simplify what is in the parentheses. So our denominator is now the cube of x plus 3, and our numerator is x plus 2, and I have 4x and a minus 4x, which is going to cancel, and I have 12 minus 8, which is 4. So that is my first derivative. When I'm making my sign chart for the first derivative, I need to look at places where that first derivative is either undefined or 0. So -3 is where it's undefined from the denominator, and -2 is where it's 0 from the numerator. Okay, so I have my number line marked off, -3, 2. I'm going to pick some sample points in each subinterval and see what happens. Something that would be easy to pick would be 0. So if I plug 0 into this, I get 8 on the top and 27 on the bottom, which is positive. Here we're positive. Notice here that my derivative was 0, and at -3 it was undefined. Okay, picking something between -3 and -2, we might actually have to work that one out. If we do -2.5 plus 2 times 4, and then -2.5 plus 3 cubed, we're just looking at whether it's positive or negative. So the numerator is negative, the denominator is positive, so overall the derivative is negative. And then if we put something like -4 in, I can see the numerator is going to be negative, the denominator is going to be the cube of a negative, which is also negative. So we are going to go positive. One thing you can also pay attention to is the multiplicity of each of these factors. So these are both odd multiplicity. This is multiplicity 1, multiplicity 3. Anytime you have an odd multiplicity, you're going to have a sign change at that number. So we can see that my derivative went positive, negative, positive, changing its sign at each one of those things. Okay, so what do those things mean about the function? Well, at -3, we have a vertical asymptote. So even though we have a sign change in my derivative, that is not going to lead to an extrema. But at -2, we have a function that changes decreasing to increasing. So at -2, we are going to have a local minimum. So from the function itself, we are going to evaluate at -2, which we've actually already done because that happened to be my x-intercept. So let's go ahead and write on here that this x-intercept is a local minimum, which I already mentioned on the previous page that I knew that the function bounced there. If it's a local minimum, then I know it has to be kind of the bottom of a valley, and it's a bounce, so I know how I'm going to approach this vertical asymptote now. I'm going to approach this vertical asymptote from the right going up. And I also know that I don't have any other extrema, local extrema, so I'm going to pass through my y-intercept. And then maybe we want to get a little bit more detailed here and find out information on concavity. Notice we're also going to have information on increasing, decreasing from this first derivative. But let's go ahead and move to concavity, and then we can try to tie it all together. So now we're going to go ahead and look at the second derivative, so f double prime of x. Again, we need to do the quotient rule. So bottom derivative of the top is just 4, subtract top. Derivative of the bottom is 3 times the square of x plus 3. Sorry, square is what that should say. All over the square, so the 6th power of the denominator. I can see that there is a factor of x plus 3 squared in both terms in the numerator, and I'm left with 4 times x plus 3, subtract 12 times x plus 2, all over x plus 3 to the 6th. Removing 2 of the factors, now simplifying the numerator of my second derivative. So I have 4x minus 12x, so minus 8x, and then I have 12 subtract 24, so subtract 12. Maybe let's go ahead and factor a -4 out of there. So again, we can see that my second derivative is undefined at -3. That's where the original function had a vertical asymptote. And it's 0 if x is -3/2. So x equals -3/2, and then x equals -3 are my important numbers here. Okay, so moving over here to my number line, I'm going to have x versus f double prime of x. And just as a reminder, our f double prime of x is -4 times 2x plus 3 over x plus 3 to the 4th. So your denominator is always going to be positive as long as x doesn't equal -3. So that's going to be an important thing to think about. So we're picking sample points. Let's pick, let's say 0, let's pick -2, and let's pick -4. And we're just running them through this function. So if I put -4 in here, -8 plus 3 is -5, multiplied by -4 is positive. If I put -2 in, -4 plus 3 is -1, times -4 is positive. So notice there wasn't a sign change on either side of -3 because the place where -3 came from, the root of this denominator, was raised to the 4th power. So there's no way you're going to exhibit a sign change on either side of that. But this 0, negative 3/2 from this factor, is raised to the first power, so I am going to see a sign change on either side of that factor. So you can see if I put 0 in, I get 3 times negative 4, which is negative. So now we're going to take a look at that number line, and first remember where our divisions were. Our divisions were at the places where the original function was undefined or where the second derivative was 0, and that splits us into 3 intervals. So to the left of negative 3, between negative 3 and negative 3/2, and then to the right of 3/2. We have a positive second derivative, so that means we're going to be concave up, and then still a positive, concave up, and then a negative, concave down. Similarly, we probably want to look at this first derivative number line and know that our function goes increasing, decreasing, increasing. Now we're going to try to put all that together. We do have an inflection point anywhere the function changes concavity. So we're going to have an inflection point at negative 3/2. We already, back when we talked about the first derivative, found the value of our local minimum by plugging negative 2 into the original function. So similarly, we need to plug the x-coordinate of our inflection point into the original function. So f at negative 3/2. Now remember, the original function was the square of x plus 2 over the square of x plus 3. So I'm putting negative 3/2 in here and negative 3/2 in here. Okay. So negative 3/2 plus 2 is a half. And then we have a square. And then negative 3/2 plus 3 is 3/2 squared. That ends up being 2 times 1/4 over 9/4. If I invert and multiply 2 times 1/4 times 4/9, I end up getting 2/9. So we have an inflection point at negative 3/2, 2/9, and then remember we had our local minimum at negative 2, 0. Okay, now let's go back to the graph and put all of this together. When I was drawing this before, I kind of guessed at the inflection point. So, and it won't let me erase now, so we'll just have to kind of fix it. So our inflection point is at negative 1.5, 2/9, which is closer to down there. So we go decreasing to a slope of 0 to increasing, but we are still concave up all the way between negative 3 and negative 3/2. Then we switch to concave down. So we switch to concave down, we pass through the x-intercept, and then we stay concave down all the way, but we still need to be in. So we're putting together all of our information. From negative 2 to infinity, my function is increasing, but to the right of negative 3/2, it is concave down. So we are going to continue and just approach that horizontal asymptote. Okay, now the next part of the graph we don't have very much information about. We know to the left of negative 3, my function is increasing, and we know that it is concave up. It would be useful to have at least one solid point on the function that I could plug in to have an idea of just placement of this piece of the graph. So I know it does something basically like that, increasing, concave up, but I want to make sure that I'm just a little bit more accurate than that. So I'm going to just pick a sample point, like I'm going to pick negative 5, and I'm going to plug it into the original function. And just do a little bit of scratch work. So I have negative 3 squared is 9, and then negative 2 squared is 4, so I have 18/4, or 9/2, which is 4.5. So at negative 5, we are at 4.5, so we're right there. And then we know that the function needs to be increasing, concave up, so here's how we tend towards that vertical asymptote, and then we also need to head towards that horizontal asymptote in the long run. Okay, some strategies that you can use to help yourself is you can actually lay down some dotted vertical lines to tell you where the important things happen. So for example, -3 was important on the original function because it was a vertical asymptote. So that one I already drew. -2 was important because that was a place where your derivative changed from positive to negative. So you could go ahead and draw a line there to indicate that something important happened there. Again, on the second derivative, -3 was important, and then -3/2 was important because that was a place where we changed concavity. Now in this function, all of that stuff happens relatively close to each other, so it's kind of hard to get that separation defined. But if we do take a look, we can see that we've got our local minimum right there, we've got our inflection point, we've got our x-intercept, which turned out to be a local minimum, we've got our y-intercept, we're approaching our horizontal asymptote on either end, and we are approaching our vertical asymptote. One of the rules you may remember from pre-calculus or algebra 2 is if the multiplicity on the asymptote is even, then it's going to be a chimney or funnel type asymptote where both of the arrows point the same direction. If you have an odd multiplicity on your asymptote, the arrows are going to point in opposite directions. Okay, now I realize that we are getting to a very long video at this point. We're in just over 21 minutes, and that was for a single problem. So I've been taking a little bit longer to explain things, kind of explaining each step as I go, but you should reasonably expect that one of these problems is probably going to take you in the neighborhood of at least 10 minutes just to work through all the steps, unless it's a very, very simple problem. Our last step is just to verify using Desmos. So we're going to make a graph in graphing software and just compare that to what we came up with. Okay, so I've got the original graph that we created on the last screen, and then I've got the function plugged into Desmos. I plugged in the original version rather than the factored version just to make sure I didn't make any mistakes. I've got my local minimum, also my x-intercept, so that's the same point. I've got my y-intercept. I have my inflection point. I have just the sample point that I chose to locate the second piece of the graph. I've got the horizontal asymptote and I have the vertical asymptote. So here's my function. This is my local minimum and my x-intercept. This is my y-intercept, my inflection point. This is just a sample point, then my horizontal asymptote and my vertical asymptote. And looking at those, I'd say that this was a pretty good job. I've got just a little bit of a difference here in how close I got to the x-axis versus the actual graph, but I do have all of my important features, the extrema, the inflection points, all of the asymptotes, the intercepts. Those are kind of all in the same place as the original graph.